This is the second half of the Chapter 3, Section 3 notes. We're still discussing increasing, decreasing, and the first derivative test. There's a warm-up question. You're given a line, and you're saying it's tangent to a curve, and you're supposed to find the point where the line is tangent to the curve. My hint is that this obviously involves the derivative somehow. Okay, so the rest of today's notes are going to involve sketching and going back and forth between sketches of functions and derivatives. So question 1 says sketch f prime on each graph below, and the relationship between the two is wherever f is increasing, the derivative is positive, and wherever f is decreasing, the derivative is negative. So if I have a function here, f, that is a straight line, and we know that f prime is always the same value no matter what, the slope of this straight line is always the same. If I start at the y-intercept and go down to right 2, I can see that the slope is -1. So to sketch f prime, I'm just going to draw a horizontal line at -1. And that is f prime. Okay. Second one is going to be a little bit more involved because we have a curve, not a straight line, but I can do the same kind of a thought process and say, where is this curve getting negative slopes and positive slopes? I've also labeled a couple important points. This point down here has a slope of 0. This point here has a tangent slope of 0, and this point here is a tangent slope of 0. So when I go to plot the derivative, I know that there's going to be intercepts at this point. Here, let's change colors. We'll put the derivative in green. 0, 0, and 0. So I already have 3 intercepts for the derivative. Now, what's happening left of this first point? These slopes are negative, so I know that f prime is going to be negative. After I get past the minimum point, I can see that the slope of the tangent lines are positive, so f prime is positive. Once I get past the origin, I know that the slopes again are negative. And once I get past this minimum point, I see that the slopes are again positive. So I know that my f prime function is going to be negative and then positive, negative and then positive. So to sketch the derivative line, I need to have a negative value, hit the intercept, have a positive value, hit the intercept, have a negative value, hit the intercept, and have a positive value. So it's going to look something like that. We don't know exactly where the maximum and minimum turnaround points for the derivatives are, so I don't know where that point is, and I don't know where that point is. We will discuss that in a future section, but as of right now, that's a pretty good sketch for f prime. So let's put a label on this and say that this is f prime. Okay. Now, one of the things I want you to notice is that blue curve, since it has 3 turning points, the original f function, I'm guessing, could be something like a 4th degree. So f is something like x to the 4th. Well, if we take the derivative of a 4th degree function, we know that we're going to get something like 4x to the 3rd. And if you look at the shape of the original black line and the derivative line that I drew, it does look like that this f prime could be a cubic because it has 2 turning points. So that does make sense. So this next set of examples is going in the other direction. You're going to be given a derivative curve, and you need to find the original f curve. So for the first one, we see that f prime is not only always positive, but it's always equal to 2. So if I have f prime is positive, we know that the f function must be increasing. And how am I going to draw a curve that has an increasing, always increasing shape? Well, I also know that since f prime is always 2, I know that the increasing rate is going to be 2, so I can draw a line that has a slope of 2. So let's say if I started at 0, 0, slope of 2 is up to right 1 or down to left 1. And that's an acceptable answer. But what's interesting about going from f prime curves to f curves is that they are not unique. This says that the slope has to be 2, which means I could have any y-intercept. So a different answer that's also completely acceptable is if I were to start at -2 or any other y-intercept, as long as I have a slope of up to right 1, up to right 1, up to right 1, down to left 1. So there is not a unique answer. It's any straight line that has a slope of +2. Any linear with slope 2. That's the answer to the first one. So pause and attempt to answer the second and the third plots before I go over the answers. So for the second example, I'm going to take the f prime graph and look for different things. F prime starts out being negative here, 0 right there, and then positive all the way over here. From here to here it's positive. Okay, so what that means is that my f plot has to be decreasing, and then maybe a max or a min, where the first derivative equals 0, and then increasing. So now I need to draw a plot that's decreasing, has a max or a min, and then increases. So I'm going to take, and wherever there's the most space, I know that at this point here, I have to have a max or a min. So I'm going to draw something that looks like this, and that is my guess for an F graph. Another acceptable version would be anything that has a minimum at x equals -2. So I could draw another one that comes all the way down here, as long as it turns around. So this one is any set of answers, any quadratic with a minimum at x equals -2. Any quadratic with minimum at x equals -2. And again, in terms of the math, if our f function is quadratic, the derivative of a quadratic is linear, so it makes sense that the plots I drew for f, the quadratics, would have a derivative that's a straight line, a linear line. All right, again, try the third one. So to sketch the f curve for the third one, I'm going to start by looking at the f prime graph and say there is a 0 there and a 0 here. F prime is -0, positive, 0, and negative in those intervals. So 0, 0, which means the f plot is going to be decreasing, increasing, and then decreasing. So it looks like between the decreasing and the increasing, we will have a minimum, and between the increasing and the decreasing, we'll have a max. So now what I need to draw is some sort of a curve that has a minimum and then a maximum at 0 and 2 respectively. So I'm going to have down, up, down, something along those lines. And again, the original f prime plot was what looks like a quadratic, so it makes sense that my f plot is going to be a cubic. The derivative of a third degree function is a second degree function. That green line is not unique. It doesn't have to be there. Any curve that has min or max at 0 and 2 is acceptable, so I'll draw another one in blue. Something that comes down, minimum there, maximum there, like that. Any of those are candidates for an acceptable. So this would be cubic with minimum at x equals 0 and a maximum at x equals 2. All right, the final example is a calculator question, and it involves a table of values. You're given two functions, f of x is x and g of x is sine x, and between 0 and pi, you'd like to know which function is greater. So it says to complete the table. I helped you out a little bit. I filled in the values for f of x. Get your calculator and fill out the values for g of x and put them in the table. Please make sure your calculator is in radians. Your calculator should always be in radians for this class. If you're taking physics, you might have to switch back and forth between radians and degrees, but calculus is always radians. So fill in the g of x table. So the values I got when I used my calculator were 0.479, 0.841, 0.997, 0.909, 0.598, and 0.141. So as of right now, it looks like the f function is always greater than the g function. So part B says use your calculator to graph the function. Use the graph to make a conjecture about which is greater function in the interval 0 to pi. So I used Desmos. You probably used your graphing calculator, but according to Desmos, it looks like y equals x is greater than y equals sine x. And if I zoom in, it's hard to tell. I've zoomed in now so that you can see that I'm at pi over 16, which is zoomed in from the previous graph, but I still can't tell which one's greater. So the calculator doesn't really do us much good. We need a more rigorous way of knowing which is the greater graph. So So the more rigorous method is to prove that f of x is greater than g of x by finding the rate of change of both of these. If I can figure out that they're tied at the start, so in other words, add another value to my table, plug in 0 to f of x, I get 0, plug in 0 to sine x, I get 0. So the two functions start out tied at 0, 0. Right here, they're tied. After that, if the rate of change of growth for g of x is greater than the rate of change of growth for f of x, that means that g of x will always be greater than f of x. So we're going to define h equal to f minus g, and then I'm going to take and find their derivatives and prove that the rate of growth of f is greater than the rate of growth of g. I may have just said that backwards, but I know for sure we're trying to get that f prime is greater than g prime, and the way we're going to compare the two is subtract them, get an h function, and prove that that h function is always positive. So here's the answer. H of x is f of x minus g of x. H of x is this. If I go to take the derivative, now I'm going to compare the rate of change of f with the rate of change of g. I get 1 minus cosine x. I solve it. Cosine x is less than 1. Well, that's true for all x's except at 0 and 2 pi. The interval that we're looking at is 0 to pi, so we know that since h of x is greater than 0, h prime of x is greater than 0, we know that the f prime is greater than the g prime everywhere, and there's our answer. It's true for all x's. Since f prime of x is greater than g prime of x, f of x grows faster than g of x, and f of x is greater than g of x. All right, those are the notes for day 7.